The radar operator's hands trembled as he stared at the scope. It was October 1977, and Senior Lieutenant Mikhail Baranov had tracked thousands of aircraft across Soviet airspace from his station outside Minsk. He knew every signature, the broad smear of a lumbering transport, the crisp return of a MiG-25 interceptor, even the faint whisper of high-altitude reconnaissance planes dancing along the border. But this made no sense. The contact appeared at 0347 hours, a normal return suggesting an aircraft roughly 40 kilometers west, altitude estimated at 8,000 meters. Standard NATO patrol pattern. Baranov logged it, sipped his tea, glanced back at the screen. Gone. Completely vanished. Not fading into distance, simply erased as if it had never existed. He checked his equipment. All nominal. He rubbed his eyes and waited. 3 minutes later, the return reappeared. Same bearing, same altitude, but now the radar cross-section read smaller than a large bird, despite the apparent size and speed suggesting a tactical jet. Baranov called his supervisor, Captain Oleg Dmitriev, who had 15 years tracking Western aircraft. Dmitriev watched the scope over Baranov's shoulder as the contact flickered in and out of existence across the next 20 minutes. When it vanished for the final time, Dmitriev picked up the secure line to Moscow. Within 6 hours, engineers from the Soviet Air Defense Forces arrived with portable spectrum analyzers and backup radar systems. They verified Baranov's equipment was functioning perfectly. The radar itself, an upgraded P-18 spoon rest system capable of detecting bombers at 300 kilometers, showed no malfunction. Yet the recorded data revealed something that violated fundamental physics. The contact's radar return varied by factors of thousands, from strong enough to classify as a fighter aircraft to barely registering above background noise. Within seconds, with no corresponding change in range or aspect angle that could explain the fluctuation. The engineers knew what stable radar returns looked like. A conventional aircraft reflects radio waves predictably based on its size, shape, and material composition. Metal surfaces create strong returns. Smooth curves scatter energy in calculable patterns. The radar cross-section might vary as the aircraft banks or turns, presenting different angles to the transmitter, but these changes follow known mathematical relationships. An F-15 Eagle measures roughly 25 square meters of radar cross-section head-on. A B-52 bomber presents a signature exceeding 100 square meters. Even the SR-71 Blackbird, designed for minimal detectability through speed and altitude, still returned a measurable 1 square meter. This contact behaved as if the laws of electromagnetic wave propagation had been suspended. One moment it existed as a solid object. The next moment the radar waves passed through empty sky. The technical report filed in Moscow 3 days later used carefully neutral language, but the conclusion was inescapable. The Americans had achieved something the Soviet Union's best physicists considered theoretically impossible. They had built an aircraft that could choose when to be visible. What Soviet intelligence didn't yet know was that the impossible radar ghost carried a designation, Have Blue, and represented the culmination of mathematics published in Moscow 15 years earlier. Mathematics Soviet engineers had read and dismissed as interesting but useless theory, with no practical application to aircraft design. The NATO radar station at Ramstein Air Base in West Germany operated under different protocols than Soviet facilities, but the confusion was identical. Technical Sergeant James Morrison had clearance for classified aircraft tracking, which meant he'd watched U-2 spy planes, SR-71 reconnaissance runs, and prototype electronics warfare pods testing new jamming systems. He understood operational security. When the range controller announced a special test window for November 16, 1977, Morrison expected another experimental radar absorbing material evaluation. Interesting data, routine procedure. The contact appeared exactly on schedule at 14:20 hours, inbound from restricted airspace over the North Sea. Morrison's APQ-120 radar, a precision tracking system designed to guide interceptors onto targets, painted a return consistent with a single-engine fighter. Range 60 kilometers, altitude 6,000 meters, speed 400 knots. He established the track, noted the data, and prepared to monitor the test profile. Then the aircraft began its approach run toward the calibration range. The radar cross-section collapsed. Morrison watched the numerical display drop from 15 square meters to 2 square meters in a single sweep. He assumed a measurement error or equipment glitch. The next sweep read 0.3 square meters. Impossible. He was tracking a jet aircraft, not a flock of birds. By the time the contact reached the calibration point directly overhead at 4,000 meters, the radar struggled to maintain lock. The cross-section fluctuated between 0.1 and 0.1 square meters, smaller than a sparrow. Morrison had calibrated this radar against known targets dozens of times. A Cessna 172 light aircraft measured 1 square meter. The AGM-86 cruise missile, specifically designed for low observability, returned 0.1 square meters. He was allegedly tracking something with a jet engine, wings, and a metal fuselage. Yet his equipment registered a signature that shouldn't exist outside of stealth missile technology. He double-checked the system diagnostics. Every component functioned normally. The radar was telling the truth. The aircraft simply wasn't there, at least not in any form the radar could recognize. The test profile continued for 40 minutes. The aircraft flew straight passes, banking turns, and simulated attack runs while Morrison's radar alternated between solid tracking and complete loss of contact. During one particularly aggressive maneuver, the aircraft turned directly toward the station, presenting what should have been maximum frontal cross-section. The radar registered 0.08 square meters. Morrison did the mental calculation. An F-4 Phantom fighter presented roughly 6 square meters head-on. This contact was 750 times smaller, despite being close enough that Morrison could hear the jet noise through the station's walls. After the aircraft departed, the range controller collected Morrison's data recordings, and classification officer reminded him that discussing the test outside secure channels would result in immediate court-martial. Morrison signed the documentation and watched the tapes disappear into a locked courier bag. He'd spent 5 years tracking aircraft across European airspace. He understood radar theory, cross-section mechanics, and the physical limits of radio wave reflection. What he'd just tracked violated every principle he'd learned. The technical report Morrison filed under special classification noted the aircraft's designation, a cryptic reference to Project Have Blue, and included raw data showing radar returns that fluctuated across 4 orders of magnitude. His conclusion, written in the carefully neutral language of military technical documentation, stated simply that the test aircraft demonstrated radar characteristics inconsistent with conventional aircraft design principles. It was the most conservative way to describe what felt like tracking a ghost that occasionally remembered to be solid. The technical intelligence report landed on Colonel Viktor Belenko's desk in Moscow 3 weeks after the Minsk incident. Belenko had spent 12 years analyzing Western aviation technology for the GRU, Soviet military intelligence. He'd studied every American fighter development from the F-4 Phantom through the new F-15 Eagle. He knew radar cross-section theory, material science, and aerodynamic design. The report from Baranov's radar station made him reach for the classified phone. Within 48 hours, Belenko assembled a team of specialists at the Central Aerohydrodynamic Institute outside Moscow. They brought the radar recordings, technical specifications of the P-18 tracking system, and weather data from the night in question. Professor Dmitry Volkov, the Soviet Union's leading expert in radar cross-section reduction, studied the data for 6 hours before delivering his assessment. The fluctuations were real. The equipment had functioned correctly, and nothing in Soviet aviation physics could explain what they were seeing. Volkov outlined the known methods for reducing radar signature. Radar-absorbing materials could diminish returns by perhaps 50%, nowhere near the 1,000-fold reduction shown in the data. Careful shaping of curves and surfaces could scatter radar energy away from the transmitter, which explained why the American SR-71 achieved a smaller cross-section than its physical size suggested. But these techniques produced steady, predictable reductions. The American aircraft appeared and disappeared like a switch had been thrown. Volkov proposed that the Americans had developed some form of active electronic countermeasure, perhaps a jammer so sophisticated it could selectively cancel the reflected radar return. The theory had one fatal flaw. The radar operators had observed the phenomenon across multiple frequencies simultaneously. No jammer could predict and cancel every wavelength in real time. The investigation expanded. KGB technical officers interviewed NATO defectors and reviewed Western aviation journals for any hint of breakthrough research. They found nothing. American aerospace companies published papers on incremental improvements to radar-absorbing coatings and minor adjustments to aircraft profiles. The Aviation Week and Space Technology magazines showed conventional designs, swept wings, rounded fuselages, traditional configurations that offered no explanation for the ghost aircraft. Belenko requested access to the Soviet Union's own stealth research programs. The files revealed modest efforts focused on coating submarines and missiles with radar-absorbing materials. Aircraft applications had been studied and largely abandoned. The fundamental problem was inescapable. An airplane needed wings to generate lift, engines to produce thrust, and a fuselage to carry fuel and weapons. These components, large metal structures positioned to interact with air, inherently reflected radar waves. Soviet engineers had calculated that reducing a fighter aircraft's cross-section below 1 square meter would require sacrificing so much performance that the plane would be useless in combat. The Americans had apparently achieved 0.01 square meters while maintaining jet performance. By December 1977, Belenko's team reached an uncomfortable conclusion. The United States had made a fundamental breakthrough in applied physics that Soviet science couldn't explain. The technical report sent to the Defense Ministry acknowledged multiple possibilities. Perhaps the Americans had discovered a new material with exotic electromagnetic properties. Perhaps they'd developed computational methods for calculating radar reflection with unprecedented precision. Perhaps they'd found a way to reshape entire aircraft around principles Soviet engineers hadn't considered. The report's final paragraph recommended immediate prioritization of counter-stealth radar development and aggressive intelligence collection on American aerospace research facilities. What the report didn't mention, because Belenko didn't yet know, was that the mathematical foundation for American success sat on library shelves in Moscow, published in Russian, written by a Soviet physicist, and ignored for 15 years. The breakthrough came from an unexpected source. In March 1978, a CIA technical intelligence officer named Dr. Kenneth Perko was reviewing translated Soviet scientific literature as part of routine monitoring of Eastern Bloc research. Most papers covered incremental work, wind tunnel studies, propulsion efficiency, metallurgy refinements. Perko nearly missed the citation buried in a footnote of a Ukrainian aviation journal. The reference mentioned Pyotr Ufimtsev's 1962 paper, Method of Edge Waves in the Physical Theory of Diffraction, published by the Soviet Radio Publishing House in Moscow. Perko requested the full text through CIA's Technical Document Acquisition Program. When the translation arrived 6 weeks later, he read it twice before reaching for the classified line to Langley. The paper presented a mathematical framework for calculating exactly how electromagnetic waves diffracted around geometric edges. Ufimtsev had solved equations that predicted radar reflection with precision Soviet and American engineers had considered impossibly complex. The math was dense, filled with Bessel functions and boundary condition analysis, but the implications were immediate. If you knew the exact shape of an object's edges, you could calculate its radar return with perfect accuracy. More importantly, you could work backwards. Design the edges first, calculate the return you wanted, then build an aircraft around those specifications. Perko sent the paper to the Defense Advanced Research Projects Agency with a priority flag. Within a week, Dr. Alan Foos, DARPA's chief scientist for advanced propulsion, was reading Ufimtsev's equations alongside engineers from Lockheed's Advanced Development Projects Division, the Skunk Works. They recognized immediately what they were seeing. American engineers had been trying to reduce radar cross-sections through intuition and trial-and-error testing. Shape a curve, measure the return, adjust, test again. It was expensive, slow, and fundamentally limited by guesswork about how radar waves would behave. Ufimtsev had eliminated the guesswork. His mathematics described the physics completely. The irony deepened as Foos investigated Ufimtsev's background. Pyotr Yakovlevich Ufimtsev had published his work at the Moscow Institute of Radio Engineering in 1962. The Soviet Academy of Sciences had reviewed the paper, acknowledged its mathematical rigor, and filed it as interesting theoretical work with no apparent practical applications. Soviet aircraft designers never used it. The equations were complex, requiring extensive computation for even simple shapes. In 1962, the Soviet Union lacked computers powerful enough to apply Ufimtsev's method to something as complicated as an aircraft. The work sat in technical libraries, cited occasionally in academic papers on electromagnetic theory, but ignored by anyone building actual hardware. American engineers had the computers. By 1975, Lockheed's Skunk Works had access to CDC 7600 supercomputers capable of performing billions of calculations per hour. Feed Ufimtsev's equations into that computational power, and suddenly the impossible became straightforward. Define an aircraft's shape as a collection of flat panels and sharp edges. Calculate how radar reflects off each edge using Ufimtsev's mathematics. Adjust the angles until the reflections scatter away from enemy radar transmitters. The computer could test thousands of configurations in hours, work that would take human engineers decades using traditional methods. The CIA's technical assessment, completed in May 1978, concluded that the United States had achieved stealth capability by applying Soviet mathematical theory that the USSR had published and abandoned. The report noted with particular emphasis that Ufimtsev's original paper remained available in Soviet technical libraries, untranslated into English until American intelligence acquired it, and apparently unread by Soviet aircraft designers who could have used it to match American capability. The Americans had won a breakthrough by doing homework the Soviets had assigned themselves and then forgotten. Ufimtsev's equations started with a problem that had frustrated physicists for decades. When radar waves strike an aircraft, they don't simply bounce off like light from a mirror. The electromagnetic waves interact with every curve, edge, and surface discontinuity. They diffract around corners, scatter from protrusions, and create complex interference patterns. Previous attempts to calculate these interactions relied on approximations that worked for simple shapes like spheres or flat plates, but fell apart when applied to something as geometrically complicated as an airplane. The traditional approach, called the physical optics approximation, treated radar reflection like light bouncing off curved mirrors. It worked reasonably well for smooth surfaces, where the radius of curvature was large compared to the radar wavelength. But aircraft weren't smooth spheres. They had wings meeting fuselages at sharp angles, engine inlets creating cavities, tail surfaces intersecting at precise geometric points. At these edges and discontinuities, physical optics failed. The approximation missed crucial behaviors, the way waves wrapped around sharp corners, how energy concentrated at intersection points, the secondary reflections that bounced between nearby surfaces. Ufimtsev approached the problem differently. Instead of approximating the entire aircraft as a smooth object, he focused on the edges themselves. His method of edge waves treated each geometric discontinuity, every sharp corner, every surface intersection, every abrupt change in shape, as a source of diffracted radiation. When a radar wave hit an edge, it didn't simply reflect. It generated a new wave that propagated along the edge, creating what Ufimtsev called edge currents. These currents then radiated their own electromagnetic fields according to precise mathematical rules. The genius was in the mathematics. Ufimtsev derived integral equations that described exactly how these edge waves behaved. For a straight edge, the solution involved Fresnel integrals and modified Bessel functions. For curved edges, the equations became more complex, incorporating path integrals along the edge geometry. But complexity didn't mean impossible. The equations were exact, deterministic, and solvable, given sufficient computational power. Input the edge geometry, length, curvature, angle, relative to incoming radar, and Ufimtsev's formulas output the precise diffracted field strength in any direction. The practical implication revolutionized aircraft design. Traditional engineers shaped aircraft for aerodynamic performance, then measured radar cross-section in expensive test facilities and hoped for modest reductions. Ufimtsev's method reversed the process. Define the radar return you wanted first. Use the edge wave equations to calculate what geometric configuration would produce that return. Then design an aircraft around those geometric requirements. The computer became the test facility. Every design iteration could be evaluated mathematically before cutting metal. The equations revealed something counterintuitive. Smooth curves, which seemed like they should scatter radar gently away, actually created complex reflection patterns, because every point on the curve contributed differently to the total return. Sharp edges and flat panels, which looked obviously radar reflective, could be arranged to channel energy in precisely controlled directions. If you positioned flat surfaces at calculated angles, the edge waves interfered destructively, canceling each other. The total radar return could drop to nearly zero, even though each individual surface reflected strongly. Ufimtsev had published this framework in 1962 with detailed derivations, example calculations for canonical shapes, and clear explanations of how the mathematics connected to physical electromagnetic behavior. Soviet engineers read it, appreciated the theoretical elegance, and filed it away. The equations required too much computation for practical use without digital computers powerful enough to handle thousands of edge integrals simultaneously. By the time the Soviet Union developed adequate computing capability in the early 1970s, Ufimtsev's paper had been forgotten, remembered only as an obscure academic contribution to diffraction theory, not as the foundation for invisible aircraft. Ben Rich stared at the computer printout and felt the weight of impossibility lifting. It was April 1975, and Rich, the deputy director of Lockheed's Skunk Works, had spent 2 years watching his team struggle with the Defense Advanced Research Projects Agency's challenge. DARPA wanted an aircraft with a radar cross-section 1% of conventional fighters. Every design his aerodynamicists proposed, sleek curves, smooth blending, refined contours, tested poorly. The radar model predicted cross-sections barely better than existing aircraft. Rich had begun suspecting the goal was physically unachievable. Then Dennis Overholser, a young mathematician in the Skunk Works radar analysis group, walked into Rich's office with Ufimtsev's translated paper and a radical proposal. Forget curves. Build the aircraft entirely from flat panels arranged at precise angles calculated using the Soviet physicist's edge wave equations. Overholser had written computer code implementing Ufimtsev's mathematics, feeding in geometric descriptions of flat-faceted shapes and calculating their radar returns. The numbers were extraordinary. A diamond-shaped configuration with flat panels angled to reflect radar away from the transmitter could achieve cross-sections below 0.01 square meters, 1,000 times smaller than DARPA's requirement. Rich assembled his best engineers in the Skunk Works secure facility in Burbank. Dick Scherer handled aerodynamics. Bill Schroeder managed flight controls. Overholser would design the radar cross-section. The specification was backwards from every aircraft development program in history. Usually, aerodynamicists designed the shape for optimal flight performance. Then radar engineers tried to reduce its signature through coatings and minor modifications. For this project, Overholser designed the shape for radar invisibility first. The aerodynamicists had to make it fly. Overholser's computer, a CDC 7600 mainframe accessed through telephone lines, processed Ufimtsev's equations for thousands of flat panel configurations. He divided the aircraft into triangular and quadrilateral facets, flat surfaces with straight edges that Ufimtsev's mathematics could handle exactly. Each facet's orientation was calculated to reflect radar energy away from threat angles. The nose panels angled downward at 72.5 degrees from horizontal. The wing leading edges swept back at 67.5 degrees. Every surface alignment followed from electromagnetic calculations, not aerodynamic preference. After 6 weeks of computation, Overholser generated a final configuration. It looked like a child's drawing of an airplane, a collection of flat triangular panels forming a diamond shape with sharply swept wings and a faceted fuselage. No curves anywhere, just angles, edges, and flat surfaces arranged according to Ufimtsev's predicted radar reflection patterns. Scherer analyzed the aerodynamics and delivered bad news. The faceted shape was aerodynamically terrible. Flat panels didn't generate lift efficiently. Sharp edges created vortices and drag. The aircraft would be unstable in all 3 axes, pitch, roll, and yaw. No pilot could control it manually. Rich made the decision immediately. Install fly-by-wire computers. Let electronic systems stabilize the aircraft artificially, making thousands of control surface adjustments per second to keep the unstable platform flying straight. The technology existed. The F-16 fighter program was already using early fly-by-wire systems. Make the computers sophisticated enough, and pilots would never know they were flying an aircraft that wanted to tumble out of the sky. Lockheed submitted the design to DARPA in July 1975. The proposal included Overholser's radar calculations showing predicted cross-sections of 0.003 square meters, 1,000th the size of conventional fighters. DARPA's evaluation board reviewed the mathematics, verified the computational methods, and awarded Lockheed the contract to build 2 flying prototypes. The project received the designation Have Blue. Construction began in November 1975 at a classified facility in Burbank, with components fabricated to tolerances measured in thousandths of inches to ensure every facet angle matched Overholser's calculations precisely. The first Have Blue prototype sat on the ramp at Groom Lake, Nevada, looking like no aircraft anyone had seen. Test pilot Bill Park walked around it in the pre-dawn darkness of November 16, 1977, checking the faceted surfaces that reflected the floodlights in harsh geometric patterns. The aircraft measured 47 feet long with a 22-foot wingspan, roughly the size of a small business jet, but weighed only 12,000 pounds thanks to the lightweight composite materials covering its faceted frame. Park had flown experimental aircraft for Lockheed since 1960. This was the strangest machine he'd ever strapped into. The first flight lasted 20 minutes. Park took off from the dry lake bed, climbed to 10,000 feet, and performed basic handling checks while chase planes monitored from safe distances. The fly-by-wire computers worked as designed, making constant adjustments to keep the inherently unstable airframe controllable. Park landed, debriefed the engineers, and declared the aircraft flyable despite its unusual handling characteristics. The real test would come during the radar cross-section evaluation flights scheduled for December. The range setup took 3 weeks. Technicians positioned radar transmitters around Groom Lake at distances from 5 to 40 kilometers, calibrated to frequencies matching Soviet early warning systems, acquisition radars, and fire control trackers. Each radar was calibrated against known targets, metal spheres of precise dimensions that produced predictable cross-sections. The measurement protocol was rigorous. Park would fly straight passes at specific altitudes and speeds while ground stations recorded the radar returns. The data would either validate Overholser's calculations or reveal that Ufimtsev's mathematics failed when applied to real hardware. December 1, 1977. Park lifted off at 600 hours and turned toward the first measurement corridor. On the ground, radar operator Thomas Reed watched his scope as Have Blue approached. The aircraft should have appeared as a solid contact at 20 kilometers. Reed's radar showed nothing. He checked his equipment. Fully operational, tracking the chase aircraft perfectly. Have Blue remained invisible. At 10 kilometers, Reed finally detected a return. The cross-section measured 0.0025 square meters. An F-4 Phantom at the same range would have registered 6 square meters. Have Blue was 2,400 times smaller. The test series continued through December and January. Park flew the aircraft through every conceivable angle and maneuver while ground radars measured the returns. Head-on approaches produced cross-sections of 0.202 square meters. Side aspects, traditionally the largest radar signature for conventional aircraft, measured 0.004 square meters. Even the worst case, looking directly up at the flat underside, returned only 0.08 square meters. The data confirmed what Overholser's computers had predicted. Ufimtsev's equations worked perfectly. By arranging flat panels at calculated angles, Lockheed had created an aircraft that scattered radar energy away from transmitters with extraordinary efficiency. The implications were immediate and staggering. Soviet air defense networks relied on early warning radars detecting incoming aircraft at 200 kilometers, giving interceptors time to scramble and engage. Have Blue's cross-section meant Soviet radars wouldn't detect it until 20 kilometers. Less than 2 minutes of flight time at typical attack speeds. By the time defenders knew the aircraft was coming, it would already be over the target. The expensive, sophisticated Soviet air defense system, thousands of radar stations, surface-to-air missile batteries, interceptor aircraft, had been rendered obsolete by geometry and mathematics. The technical report submitted to the Pentagon in February 1978 concluded that Have Blue had achieved radar cross-sections 1/10,000th the size of conventional fighters. The aircraft validated stealth technology as operationally feasible. The Air Force immediately authorized development of an operational stealth fighter based on Have Blue's design principles. The program received the designation F-117 Nighthawk. Production would begin in 1980. Creating a fleet of aircraft invisible to Soviet radar built using mathematics a Soviet physicist had published and his country had ignored. The Soviet response began with disbelief, then panic, then desperate improvisation. By mid-1978, KGB technical intelligence had assembled enough fragments to understand what the Americans had achieved. Satellite photographs from Lockheed's Burbank facility showed unusual aircraft shapes under construction. Angular, faceted forms, unlike conventional designs. Intercepted communications between Air Force test ranges mentioned radar cross-section measurements in the thousandths of square meters. Soviet aerospace engineers reviewed the evidence and reached an uncomfortable conclusion. The Americans had solved radar invisibility not through exotic materials or electronic jamming, but through fundamental design principles Soviet science had missed. The Sukhoi Design Bureau received emergency funding in August 1978 to develop stealth retrofit programs for existing aircraft. Chief designer Mikhail Simonov assembled his best aerodynamicists and radar specialists with a straightforward mandate: reduce the radar cross-section of the Su-27 fighter, currently in development, to match American capability. The team spent 6 months studying the problem before delivering their assessment. Impossible. The Su-27's design was locked. Conventional swept wings, rounded fuselage, large vertical stabilizers. These components were optimized for aerodynamic performance and couldn't be fundamentally reshaped without redesigning the entire aircraft from scratch. Applying radar-absorbing coatings might reduce the cross-section by 50%. American stealth represented thousand-fold reductions. The gap was unbridgeable through incremental modifications. The Mikoyan Design Bureau pursued a different approach. Rather than retrofit existing designs, they initiated studies for a completely new stealth fighter incorporating faceted surfaces and angular geometries. The engineers faced immediate problems. They understood the goal, arrange flat panels to reflect radar away from enemy transmitters, but lacked the mathematical framework to calculate optimal configurations. Without Ufimtsev's edge-wave equations, they were reduced to educated guessing. Build a faceted model, measure it in a radar test facility, adjust the angles, measure again. The process was slow, expensive, and produced mediocre results. By 1982, Mikoyan's best stealth prototype achieved radar cross-sections around 0.5 square meters, 50 times larger than American aircraft. The Soviet military research establishment also prioritized counter-stealth radar development. If Soviet aircraft couldn't match American invisibility, perhaps Soviet radars could be modified to detect stealth aircraft. Phasotron, the leading radar design bureau, investigated multiple approaches. Lower-frequency radars operating at longer wavelengths might detect stealth aircraft better than traditional high-frequency systems. The physics was sound. Ufimtsev's edge-wave effects diminished at longer wavelengths. But lower frequencies meant larger antennas and poorer resolution. A radar that could detect stealth aircraft at longer range might be unable to guide missiles accurately enough for engagement. Bistatic radar configurations offered another possibility. Traditional radars transmitted and received from the same location. Bistatic systems separated the transmitter and receiver, potentially catching radar energy that stealth aircraft reflected away from the transmitter. Soviet engineers built experimental bistatic networks around Moscow and key military facilities. The systems worked, detecting test aircraft with reduced cross-sections more effectively than conventional radars. But bistatic networks required extensive infrastructure, multiple synchronized stations covering overlapping zones. Deploying such systems across the Soviet Union's vast territory would cost billions of rubles and take decades. By 1985, Soviet military planners faced a grim calculation. The United States had achieved a fundamental technological advantage in aircraft design. Matching that advantage would require either discovering the mathematical principles Americans were using, principles Soviet intelligence suspected came from open Soviet publications, or investing massive resources in counter-stealth systems of uncertain effectiveness. Meanwhile, American F-117 production continued. Intelligence estimates suggested the U.S. would deploy a fleet of 50 to 60 operational stealth fighters by 1990. The Soviet Union's air defense network, built at enormous expense over 40 years, faced obsolescence against an enemy that had learned to be invisible using mathematics published in Moscow. Pyotr Ufimtsev learned about his role in American stealth technology the way most Soviet citizens learned surprising news, through carefully worded questions from KGB officers. It was 1985, and Ufimtsev, now retired from the Moscow Institute of Radio Engineering, received a visit from two men in dark suits who wanted to discuss his 1962 paper on edge-wave diffraction. They showed him satellite photographs of angular American aircraft and asked if his mathematics could predict radar signatures of such shapes. Ufimtsev studied the images and confirmed what the officers already suspected. Yes, his method could calculate the radar return of faceted geometric forms with precision. It was exactly what he'd published 23 years earlier. The officers asked why Soviet aircraft designers had never used his work. Ufimtsev explained patiently. In 1962, applying his equations to complex shapes required computational power the Soviet Union didn't possess. He'd published the mathematics as theoretical contribution to electromagnetic diffraction theory, not as practical design tool. By the time Soviet computing capability matured in the 1970s, his paper had been forgotten, filed away in technical libraries as interesting but impractical academic work. The Americans apparently had found it, recognized its value, and built an entire weapons system around mathematics Soviet engineers had dismissed. The irony wasn't lost on Soviet leadership. At a Ministry of Defense technical review in 1986, Marshal Sergei Akhromeyev summarized the situation with unusual bluntness. The United States had achieved strategic advantage by reading Soviet scientific literature more carefully than Soviet engineers had read it themselves. Ufimtsev's paper had never been classified. It was openly published, available to anyone. American intelligence had simply done better homework, recognizing practical applications Soviet experts had missed. The Soviet Union now faced aircraft it couldn't detect using radar systems that had consumed substantial portions of the defense budget for decades. The operational consequences became clear during the 1991 Gulf War. American F-117 stealth fighters flew nearly 1,300 combat sorties into Iraqi airspace protected by Soviet-made radar systems, the same SA-2, SA-3, and SA-6 surface-to-air missiles deployed around Moscow and Soviet military facilities. Iraqi air defenses, trained by Soviet advisors and operating Soviet equipment according to Soviet doctrine, never successfully engaged a stealth aircraft. The F-117 struck targets in Baghdad with impunity, while conventional American aircraft faced heavy surface-to-air fire. The demonstration was definitive. Soviet air defense technology, built around detecting conventional aircraft, was obsolete against enemies who understood edge-wave diffraction. The mathematical foundation of this obsolescence sat in Russian libraries, published in Russian, written by a Soviet physicist for Soviet engineers to use. Ufimtsev's method of edge waves had been freely available since 1962. No espionage was required. No classified information was stolen. The Americans had simply recognized the value of open scientific literature, translated a paper their adversaries considered impractical theory, and applied it with computational resources and engineering discipline. The Soviet Union's failure wasn't a lack of scientific capability or theoretical understanding. It was a failure of imagination and investment, the inability to see how theoretical mathematics could reshape warfare when combined with sufficient computing power. By 1991, as the Soviet Union collapsed, Western aerospace publications finally revealed the full story. Articles in Aviation Week and technical journals from Lockheed confirmed that F-117 design had relied heavily on Ufimtsev's diffraction theory. The equations that made American aircraft invisible to radar had been published in Moscow, reviewed by Soviet scientists, and filed away as interesting but useless. The Americans had won by being better students of Soviet science than the Soviets themselves, turning theoretical physics into operational hardware that helped bankrupt an empire trying to defend against invisibility achieved through its own discarded mathematics.